Let's start on bot plot. We will continue on bot plot. Before we stop, before the semester break, we learn that bot plot is important. Bot plot consists of many components. If you can, we can go back to this. Remember that we have bot plot for GS equal to K, GS equal to S, 1 over S to power of N, S over A plus 1. See the special form, S over A plus 1. And also we have 1 over S over A plus 1. So we have this, we have shown the magnitude and also the frequency, the phase response of each component. And today we will look into how can we combine all the components. We are now trying to sketch the bot plot. Using the approximation, using the straight line approximation. Remember that what we did here is just to sketch and to show that later the sketching is similar to the actual one. I just added this slide. Initially, it was in your slide. This one, draw the bot plot, GS, all this transfer function. But I just add this one. We will start with a simpler one in order to show how can we sketch bot plot. In doing this, I asked you last time to, if possible, to have a semi-log graph. If you can print, if you have with you, will be good, because we are going to do the sketching. Good if we can do together. Okay, so let's start. Draw the bot plot for the system. Draw here is actually sketch. Okay. Sketch the bot plot for the system given 1 over S plus 5. So here we have 2 poles and no 0. In sketching root locus, first step is to do what we call normalization. Normalization. What this means? Because remember that each component has its own form. So we want to transform them into the form that is easier for us to draw. Okay. So here, what we need is to show 1 over S. I want to change this. I want to transform this. Remember, the one that we prefer is S over A plus 1. We want to make sure we have 1 here. Okay. So S plus 5 here can be written in this form. S, we take out 5 and S over 5 plus 1. Okay, so we have in this form. This is actually equal to 1 over 5. I can bring 5 in the numerator, 1 over 5 S over 5 plus 1. Okay, So this is first step we call normalization. If we have many poles, then all pole has to be normalized. S is we maintain because we have 1 over S. In here, we know that we have 3 components. Component 1, component 2, component 3. 3 components. And we will draw, we have to sketch for all the components. Okay. Okay, the first component GS equal to 1 over 5. Okay, if you check GS equal to K in your notes, first we get the magnitude is 20 log 1 over 5. Okay, 20 log K in dB, magnitude in dB. If you check, if you calculate, it will be about minus 14 dB. Okay, minus 13.98, minus 14 dB. And then the phase, before that, then the phase, normally we put JG omega, okay, sorry. JG omega is equal to 0 degrees. Okay, always 0 degrees. So that is the first component. The second component, number 2, I take ds equal to 1 over s, this one. And if we take in transfer in frequency response, it will be 1 over j omega. If you check our notes before, here we have 1 over s. Remember? 1 over s here. 1 over s we derive here. Then we say we obtain this. 1 over s is a line, straight line, minus 20 dB per decade here. Okay, and it crossed 0 dB at 1 radian per second. So you have to know this. 1 over s, then this is the one. And the magnitude, the phase, always minus 90 degrees. That is for 1 over s. Okay, so please look into this. So if we plot here, omega in radian per second. It's 1 here, 1, 0 dB. So it will be like this. Okay, minus 20 dB per decade. And the phase, minus 90 degrees. So that is component 2. Next is the third component, GS Number 3, GS is 1 over S over 5 plus 1. Okay, check your note when we have GS over 1, S over A plus 1. Remember that A here is called break frequency. A S over A plus 1. See, A is break frequency. It starts from 0 dB up to A here. Then it go down with a straight line minus 20 dB per decade. It go down because it reduced because minus 20 dB per decade. And the phase is like this: 0, then minus 45 degrees per decade until 10A, then it stop at minus 90 degrees. So we have to know this. Okay? And the most important point here is A. A is the break frequency. And this is why we try to, we first normalize the transfer function from S over S plus 5 into S over 5 plus 8. S over 5 plus 1. Because we want to have in this form, then we can obtain the dot plot in this. It is obtained in this form. If we have S over A plus 1. So for here, you want to plot this is for magnitude in dB. Here A here 5. 1 decade before is 0.5, 50, and so on, 500. Zero dB here. So from before the break frequency is 0 dB. After that, it go to like this, minus 20 dB per decade. That means here is minus 20 dB. 1 decade is reduced by 20. Here, minus 40 dB. Similarly, we can also draw for the phase. We can look into the nodes. Here 0.05. We have minus 45 degrees, 0 degrees, minus 90 degrees. It is from here to 1 decade before break frequency. Okay. It starts from here, and the break frequency is 45 degrees. At 1 decade after that is 90 degrees. So it will be like this, 45 degrees. So this is a line minus 45 degrees per decade with a slope of minus 45 degrees per decade. This is the third component. Any question before we continue?
No, doctor.
Okay, let do on this paper. On this we call semi-log graph paper. Hope you have this. Before that, I just want to clarify with you. We will not ask you in the exam on drawing this one. We will not ask you to sketch on this board plot. But I make effort to teach you, to show to you, so that your understanding can be improved. It will not be asked in the exam. We will give you the board plot. Okay, but you have, of course, have to know how to read. Hopefully, by doing this, your understanding can be enhanced, and also for your knowledge on sketching root log board plot. So this is, I'm sure you have seen this. On the x-axis is a log scale. Okay, you can see from this is called 1 decade. This one decade. So we have 1, 2, 3, 4, 5, 6, 7 decade in this graph. Then y-axis is a normal scale here. Okay, normal. You can see the log scale on x is not equal, not even. So it start from a big scale, then reduce in 1 decade. Okay, but normal scale all the same. Okay, let plot for magnitude. So I will do here magnitude. This is the axis for magnitude in dB. This is omega in radian per second. And for board plot, for the log scale, we have to decide the scale for omega, and also, of course, for magnitude. And omega have no zero. So you couldn't find in dB, so in radian per second, 0. No, it will be, we have to decide. Let's say I put this one 1 radian per second. 1 decade before that is 0.1. Here 10. And we have to know the range, and the range should cover the break frequency. Okay, remember our break frequency is 5. So it's around here, 5. So if this is 10, 100, 1,000, 10,000, 0.01, 0.001. So we will use the same scale for also for for phase. This is phase in degree. Then this is dB, 40 dB minus 0 dB here, minus 60 dB. 0, so degrees, minus 45, minus 90, minus 135, minus 180 degrees. Okay, the scale also, we have to decide a proper scale. Okay, let's start by looking into the first component. This is the first component. ES 1/5. The magnitude is minus 14 dB. Minus 14 dB. 14, this is 10. I just sketch, huh? This is minus 14 dB. So this is component 1. Minus 14 dB. And the angle is 0. The phase is 0. So 0 is here for component 1. Then, second component, 1/s. 1/s, we know is minus 20 dB per decade line, straight line. So it cross 0, it cross here 0. And 1 decade, it will be 20. So here 20 minus 20, I'm sorry. 20 here. 20. $40 here and 60. So it will be like this. Okay, minus 20 dB per decade. And the phase always 90 degrees. So this is the phase for second component. This is second component. Sorry, I make mistake. Second component should be going at 1/s. Like this. Okay, going up. See, because I choose not a proper scale, I could not complete up to the axis. Here is 1/s. Okay, the third component, 1/s/5 plus a plus 1. The third component, as we know, use break frequency 5. Before I forget, how to read this, this is one, here is 2, 3, 4, 5 until 10. Okay, similarly here, if 0.1, the next one is 0.2, 0.3 until 1. So that's how to read omega in radian per second. So 5 is here, 1, 2, 3, 4, 5. 2, 3, 4, 5. This is the break frequency 5. Okay, and here 50. 1, 2, 3, 4. 50 here. Therefore, the third component, we know it starts from 0, here 0, until the break frequency. Then it will be a straight line of 20 dB per decade. At 50, it goes to minus 20. At 500, 2, 3, 4, 5, 500, it goes to minus 40. So it will be like this. This is the third component. And let's see also the phase. Phase is a bit more complicated. Here 5, which is the break frequency. We have to identify 1 decade before 5, which is 0 0.5. 0.2, 0.3, 3, 4, 5. 0 0.5 here. And 1 decade after, 50. Okay. If you check the note, it starts from 0 degree until 0 0.5, which is 1 decade before the break frequency. And at the break frequency, it will be 45 degrees, minus 45 degrees. After that will be 90. So it will be like this. This is the third component. Any question before I proceed? It is not easy to teach this. I mean, not easy to teach this online. Hope you, if you have questions, just ask. If you just see, of course, you cannot do it. You have to do it. Okay, this is the component that we have. And we now going to the last one, to the last step, which is more difficult. We want to obtain the final one for all. Remember what we did now is just for each component. We have 3 components. Okay, but we need to do for all components. We need to add to get the final one. How to do it? Remember that this is log, because in log we can we actually have to multiply all the pole if we have, and multiply all the zero. In this case, no zero. Therefore, we can, because of log, if we multiply, then we add. If we divide, we minus, and it's already in dB. So the magnitude is obtained, the final magnitude is obtained by adding all the components. How to add? Okay, let's see here at 0.1, because I could not finish, because 0.01 we need more higher scale. let's say 0.1. 0.1, here we have three components. Component 1 is 0. Component 3 is 0. Component 2 is 20 dB. Component 1 is minus 40 dB. Here, minus 40 dB. So if we add, it will be 20 plus 0 minus 40, it will be 6 dB. So it will be here, 6 dB. Add together. Okay, how to add actually is by adding the slope. You see here, at this point, at this region, we have slope minus 20 dB per decade. Here slope 0, here slope 0. So it will be minus 20 dB per decade. Okay, until here also no change, until 5. When at 5 dB, the third component become minus 20 dB per decade. So it will be like this, 6, here 6, 20, 14. It will be like this, 10, 4, this is minus 20 dB per decade. So we have to draw a line minus 20 dB per decade. Okay, up to 5. Because after 5, the third component become minus 20 dB per decade. Initially it was 0 slope, but now minus 20 dB per decade. So after 5, it will be added. It will be minus 40 dB per decade. That means here 34, here maybe 30, at 50 become 30, 70. 70 is here. So it will be like this. Different slope, minus 40 dB per decade. So this is, if I continue, it will go going down. It may also overlap with the phase. I will stop until here. This is the final GS. Okay, for the magnitude for GS. I hope you try after this. If you have questions, just ask. As I said, not easy actually to understand this, but please try to do. And you have to understand the slope, minus 20, minus 40. Okay? That is important. Although again, although this will not, you will not be asked to draw this, but the slope you have to know the slope, how to draw the slope. Because in designing controller, we need to know the slope, minus 20, minus 40, and so on. Okay, let's continue with the phase. Phase, again, also we add the slope. Component 1 here, we have 3 components. Initially, all component 1 and 3 are 0. But we have minus 90. We add, we have minus 90 here. till 0.5. Okay. Component 1 always 0, so it will be just 2 plus 3. So until 0.5, we see that it going down, minus 45 degree per decade. So that means here at 5 is minus 135. And at 50, it will be minus 180 degrees. Because it's going down by 45 degrees per decade. It will be like this. And then no slope, all 0. So this is GS. Minus 45 degrees per decade here. Any question? So this is the final one. GS for magnitude and GS for the phase. Please try at home after this. So that if you have question, you can ask. Let's move to here. I will not do again, just sketching later. Okay, I want you to first, we want to sketch the dot plot for the system with K3000. K3000. In order to plot, we need all the value. So now I want you to do first normalization. Okay, now all normalize the transfer function. How to normalize? We have to, K is 3000. We want in terms of this, S plus 3 plus 1. S over 3 plus 1. Therefore, we need to take out 3. S, we maintain S. We take out 10, S over 10 plus 1. Then 50 S over 50 plus 1. This is what we call normalization. Then that means 3,000. 3 over 500. S over 3 plus 1. S over 10 plus 1. 50 plus 1. So 6, that means 18. 18 S over 3 plus 1. S over 10 plus 1. 50 plus 1. Okay, here we have 3 poles, 1 0, and also 1 gain or 1 constant. That means we have 5 components. Component 1, component 2, 3, 4, 5. If we want to sketch a box plot, then we have to sketch initially each component. Okay, similar to this, in which we did one by one, step by. Here we have 3 components. Here, of course, more difficult because we have 5 components. Okay. You can try to do it step by, one by one. Then finally you can add in order to get the final one. You have to know the concept. Again, it will not be asked in the exam, but you have to know the concept on how to sketch each component and then how it is added together to get the final one. We take a break, 10-minute break. Any question before we take break?
No.
I hope you have this graph and be familiar with this graph. Have you used this graph before? Semi-log graph.
No, doctor.
Okay, if not, I thought in communication you use. Communication. In learning filter, do you use this graph? Okay, if not, please be familiarized with this graph. Okay, if you want to buy this graph, you can go to there is in stationery shop. Ask for a semi-log graph. Remember, here is a log scale, so you have to familiarize with this is, if this is 1, then 0.1. Here is 10. Then how to read the scale. Although, as I said, you will not be asked to draw or to sketch, but you will be given the drawing, the board plot. You have to know. You have to understand and know how to read from this graph, from this log scale, from this semi-log graph. So please be familiarized with this. We will take a 10-minute break and continue with board plot. After this, we want to show you what is the importance of Bode plot. Okay, it will be no use if we just draw. What is the use? What is the application of Bode plot? So after the break. Before break, we have looked into this problem in which we want to sketch the Bode plot, and it can be first we have to do normalization, and then we have 5 components, and we have to plot each component. Finally, we have to add components, all the components for magnitude and also for the phase angle. You have to do on a semi-log graph, and this is the actual one. I plotted from in MATLAB and extracted here. So it will be like this. Of course, the one that we will draw based on straight line approximation will not be accurate like this. Okay. So just to show you, later in the exam, you will be given a Bode plot like this. Of course, with a scale. Normally, we plotted on a semi-log scale. Okay, like this, it will be given to you, and okay, 3,000. Remember, this is for 3,000 SS plus and 50 and 50. Okay, this is GS. Bode plot for this GS. Here in MATLAB, normally it is default is 4 decade. Here is 10 to the power of 0 is 1, 10, 100, 1,000 radian per second. Here omega radian per second. Okay. 0 dB, this is magnitude, and phase in degree. Okay. We can see that the magnitude y like this because 1 over s. Okay. Here 1 over s. 1 over s here, it will start by minus 20 dB per decade. Okay. The starting point is determined by, of course, the gain. 20 log 18. Okay, gain K. Okay, so 20 minus 20 dB per decade, then we have to add, sorry, here should be S plus 3. 1 0, 3 poles. And let's see also the phase here. The phase, just to perhaps you know, but just to inform you that each pole contribute to minus 90 degrees. Each 0 contribute to 90 degrees. I was talking about at the end, it goes to minus 90 or goes to 90 degrees. For example, 1 over S, that means one pole is always minus 90 degrees. If we have 1 over S plus 10 S over 1 over S over 10 plus 1, we will have at the end minus 90 degrees. Okay, although it starts from 0. If we have S plus 3, a pole like 0 like this, S plus 3, it will be 90 degrees. Therefore, if we look into this equation, here contribute 0 degree. Again, K always 0. Here at the end, it go to 90 degrees. Because 0. 1 over S will be minus 90 degrees, minus 90 degrees, and minus 90 degrees. So if we total up, it will be 90 minus 270 degrees. It will be minus 180 degrees. So it is reflected here. You see here the phase graph. It starts from minus 90, then finally it go to minus 180 degrees. Okay, this is because the trans function have 1, 0, 3 pole. Total up, finally it is minus 180 degrees. So based on the phase plot, you will know the differences, how many pole and 0, the difference between them. Of course, it is not easy to find the location, but you know how many different between pole and 0. And because each contribute to 90 or minus 90 degrees. Right, so if you have time, you can try to plot on a semi-log graph, and then you can also compare with the actual one. Of course, it will be not similar, but the pattern, you can see there is some similarity in the pattern. Also here we know that the break frequency is 3. 3 here, the break frequency. We have also 10, also another break frequency, and 50. Here 50. 50 is also another break frequency. So you can see later the difference. You can see from here, it go to then it change the slope until 10, then change again. So that means the break frequency, as we did before, the slope is changing at the break frequency. Also for the phase. Right, now we want to look into the application of Bode plot. How can we use Bode plot in order to analyze and also later to design a controller? We will start first on using Bode plot to analyze the system. Okay, although the Bode plot in frequency domain and our system, our real system, normally in time domain, later we can use Bode plot, although in frequency domain, to estimate the result in time domain. The first, stability. You know, stability is very important. In time domain, we use, in order to determine stability, we have to know the location of poles, in which to be stable, all poles must lie on the left half plane, must be all negative. And also we can use Rosowitz criteria in order to check or to determine stability. Okay, in Bode plot, stability for a closed loop system. Okay, we refer to this. This is a closed loop system. In particular, this is a unity feedback closed loop system. In Bode plot, what we will draw, what we will obtain is a Bode plot of an open loop system. What we will draw is Bode plot for open loop. Open loop means just this. Okay, open loop transfer function. We will draw open loop, but the good thing about Bode plot, we can estimate, we can analyze the closed loop based on the open loop system. Remember, what we draw is open loop transfer function. But we can predict stability and other thing later based on the open loop system. We predict the closed loop system characteristic. I did not go into detail in theory, but this is the one that you have to know. What we plot or what we sketch is an open loop transfer function, but later analysis, the data of the open loop can be used to analyze closed loop system. So stability of a closed loop system can be determined using Bode plot of an open loop system. We draw Bode plot of GS, then we can estimate or determine stability of a whole system, closed loop system. So this is the statement for stability. A closed loop system is stable if the magnitude is less than 0 dB. That means magnitude is 0 is negative dB, less than 0 dB at frequency where the phase is 180 degrees. Normally, it is mentioned here plus minus, but normally minus 180 degrees. Because minus is pole. Okay, going up, we know that positive for 0, normally minus 180 degrees. So a closed loop system is stable if at frequency of the phase minus 180 degrees, the magnitude is 0 dB. It's less than 0 dB. That is a statement for stability in Bode plot. Okay, we'll see one example. Bode plot, use Bode plot to determine the range of K within which the unity feedback system is stable. This is the unity feedback. For example, given GS let's say this is GS, K S plus 2, 4, and 5. Okay, from here we know we have 3 poles, no 0. We will straight away know that the system, the phase angle will finally go to minus 270 degrees. Because this is minus 90 degrees, and minus 90 degrees. You see, this is the exact Bode plot. It go to minus 270 degrees. We know that we have 3 poles and no 0. The difference must be 3. Okay. That is one information that we can straight away obtain by looking into the number of pole and 0. We have to do a normalization in order to plot. Okay. 2s over 2 plus 1, 4s plus 4 over 1, 5s over 4 plus 1. So it will be k over 40 s over 2 plus 1. Sorry, 5 should be 5. Right, see, this is what we call normalization. And then usually based on this, we have to determine k in order for us to plot, to obtain a dot plot. K is needed. Okay. In this case, it is mentioned here for convenient, choose k equal to 40. Why k 40? Because if we use 40 here, then it will be 1 over. Then it's easier. 20 log 1 is 0. If you use k equal to 1, that means it will be negative. It will be, we have another component, which is 20 log 1 over 40. If we choose k equal to 40, that means 20 log 1 is 0. Okay, so the phase also 0, the magnitude also 0. It depends what the value of k we want to choose. It will give the same answer later. But here it is, as I mentioned, for convenient, we use k equal to 40. Right, with k 40, this is the dot plot. The magnitude and also phase in dB and also in degree. Okay, based on this, when k 40 is the system stable, when k 40 is the system stable, anyone can have, based on the statement, the stability statement before in the previous slide. Is the system stable?
Yes.
How can we check stability?
Magnitude less than 0 dB.
Again? Sekali lagi?
Magnitude less than 0 dB.
Magnitude less than 0 dB. What we did is first, we have to check the phase. Frequency where the phase minus 180 degrees. Minus 180 degrees is here. Okay, we check. Go here. This is a point where 180 degrees phase and omega is here. Omega is, this is 1, here 10, 6.5 maybe, radian per second. In between 6 and 7, 6.5 radian per second. That is the frequency where phase minus 180 degrees. Then we go up at the same frequency and check the magnitude. To be stable, when phase 180 degrees negative, the magnitude is less than 0 dB or negative. Okay, in this case, the magnitude is equal to, you can see that about minus 20 dB. Therefore, the system is stable when K40. Remember that we plot using K40, and the system is stable. Any question at this moment? Stability is very important and surely will be asked in the exam. Any question?
No.
Doctor, I have question.
Yeah.
How do you get omega equal to 6.5?
This is 1, right? 10 to
okay.
power of 0. 1.
1.
1. Here 1. Here 10 to power 1. 10 here.
Okay.
10. So 1 decade, here 0.1. Here 1,000. 100. 1, 2. Maybe not that clear. Sorry, this is from MATLAB. Difficult to make it, to show the 2, 3 here.
Oh, 3, 4,
4,
5, 6.
5, 6, 7, 8, 9, 10.
Yeah, estimate the middle of the 6
Yeah,
and
so
7,
it
right?
is
Okay,
between
6
6
and 7.
and 7. So I just put 6.5.
Okay, understand.
So in the exam, all students will have will have to estimate maybe 6, maybe 7. We will accept within certain range. Okay. It couldn't be 6.54. No. It just one, maybe just one decimal place. In the exam, we will give you a more a better one. Is like this. The one on semi-log graph. This is difficult to read. Okay, look, let's discuss more on stability. So in Bode plot, for magnitude, 0 dB is normally used as reference. 0 dB is important. Okay, you can see that we want positive or negative dB. And in phase usually minus 180 degrees is also important. So in magnitude 0 dB, in phase minus 180 degrees. So if I have this system, a dot plot of a system here, is this stable? Is the system stable? System A, I call system A. Is system A stable?
Yes, doctor.
It is stable.
Doctor.
Yes, doctor.
Yes. Yes, it is stable. Because why? Why stable?
It's less than 0 dB
Magnitude
less than
after
0
dB.
180.
At 180 degrees,
Yes.
you can
Magnitude
see
less than 0
here
dB.
is negative, right? So it's stable. How about this? B. Same phase, but different magnitude. Is B stable?
No, doctor.
In this case, B is unstable. Because it's positive here.
Magnitude more than 0 dB.
At 180 degrees is more than 0 dB or is positive. And we also have, if we have in between system C, same phase, but different magnitude, and when 180 degrees, it is 0 dB. Okay? This is called critically stable. Or sometimes people call marginally stable. A critically stable is a case where the pole is on the imaginary axis. Pole on the j omega axis. System is critical. Is critically stable, and usually the damping ratio zeta is 0, and the system is oscillatory. It's like sine wave or cosine wave, cosine signal. So based on phase and magnitude, you can determine whether the system is stable, unstable, or marginally stable. Okay, now I want to return back to here. I would like to erase, but no, not able to erase. Okay, let return back to this. The system here is GS is 40, S plus 2, 4, 5. And the system is stable. Stable because here 180 degrees. And here about 6.5 radian per second. Yeah, it's about 20 dB positive, minus 20 dB. So it's stable. Okay, what happened if initially it was like this, K. Okay, my next question, very important question. What happened if we change K? Initially 40, what happened if I use, this is just example, K 100? What happened to the phase and what happened to the magnitude? Now I change, K become 100. Okay, first, what happened to the magnitude, to the phase? Here we have a 4 component. Component 1, component 2, 3, and 4. Right? 2, 3, 4 maintain. Only component 1 change. Because maybe 440, I change to 100. So component 1 change. But component 1, we know the gain is 20 log K, right, for component 1, and the phase is always 0 dB. Sorry, 0 degree. Always. Because K is lie on a real axis, 0 dB, positive. Therefore, if we use K, different K, if K 100 or K 1000 or 10,000 or any value of K, the phase will be 0 due to that component K. So there will be no difference on the phase because K contributes 0 degree. No change in K, no change in the phase. Then any value of K will make the phase similar to the previous one. Now we want to see what happened to the magnitude. If I use a larger K, that means K, for example, K 100, it will be 20 log 100. 100 is 20 log 100 is 2, become 40. It's surely more than 40. Okay, 40, 20 log 40 is less than 20 log 100 is 2, 20 log 40, perhaps 1 point something. So if we increase K, if we use higher K, all this will go up. the magnitude will go up, will increase. Okay, but all will be increased in using the same magnitude in parallel. So it will be increased like this. This is the amount of the increase. Here, the difference. All will be the same. All increase by that point. By before it was 20 log 40, we changed to 20 log 100. So all increase by 20 log 100 minus 20 log 40 dB. So all in dB. So all will increase by this value, the difference. But phase will be the same. If we reduce K, for example, if I use K equal to 1, initially it was 40, I reduced to 1, it will be reduced. All will reduce by, will be like this. Okay, by the difference here. Difference is 20 log 40 minus 20 log K, 20 log 1. Okay, 20 log 40 minus 20 log 1. So reduced by this. If we use a less K, less value of K. Therefore, one important information here, if we change K with is called letter gain, the magnitude will change up and down. If we increase, we're going up. If we reduce, going down. In parallel, all points will be increased or reduced by the same point, by the same value. So it will be in parallel, but the phase will have no difference, will remain, because K contributes 0 degree. Right? Any question before I proceed?
So, Doctor, hello.
Yeah.
If we change the K, it means we change the stability of the system also.
Yeah, of course. K, we will go later after this.
Okay.
Because when we change K, we change K, it will go up and down. It will be later like this, right? It can be like this. This is certain K, another K, but the phase is the same. So perhaps initially like this, then it can increase up here and also it can reduce.
Okay, Doctor.
Okay. Okay. Let discuss what your friend mentioned just now. That is we can see the question here. Okay, so we haven't complete the question. We haven't. We haven't. We just check stability just now at K40, but the question is determine the range of K for stability. Okay, we know K40 is stable, but what is the range? Until when the system stable? That can be used, obtained by using the plot. Okay, again, here. Now we want to check the range of stability. We know at K40, system stable. This is K40. At here, 6.5. 6.5 here. Here, 20 dB. Okay, if K as plus 2, 4, and 5. When I increase K, let's say K50 or K60 or K100 or K1000, it will increase. The gain or the magnitude will increase until increase here until this point. Right? What happens if at 6.5 radian per second here, when the phase is minus 180 degrees, the magnitude is here. What happened? If we increase by this, so what is the condition here?
Critically stable.
So the system is critically stable. If we increase from here to here, that means I increase from minus 20 dB to 0 dB. Okay, all increase by 20 dB, 20 dB, 20 dB, all. Here also increase by 20, here also increase by 20 dB. Okay, that means I add the initial one, I add 20 dB. All will increase in parallel by 20 dB. That's why initially 0, I plotted here at 20 dB. 20, 20, up to here, maybe a bit different. Then from here, important point, from minus 20, it becomes 0 dB. And all increase by 20. And at this point, the system is critically stable. The next question is, what is the K here? Here we know that we plot K40 and the system stable when K40. What is the K here? What value of K that make the magnitude like this? We can obtain by using 20 log K, I call K, K1. I want to differentiate from this K, I use K1 equal to 20 dB. That means I want to find K that increase the gain or the magnitude by 20 dB. Okay, then we can use log K equal to 1. 20 over 21, and then K, of course, if you anti-log, it will be 10. Log 10 equal to 1. K1 equal to 10. So if we use K1, if we increase K1 or use K1 increased by 10, it will be increased by 20 dB. Then the value of K is equal to initial K multiplied with K1. Because we cannot use just K1 because initially it was 40. If initially 1, then we can directly use this value as the K. Because we already have 40, we have to multiply with we have to multiply K1, which is 10, with 40, is 400. So here, if we use K400 here, the magnitude will be like this, and the system will be critically stable when K400. So the range of stability is K between 0, because 0 will be down, less than 40 will be almost will be, of course, will be stable, but it will be going down, then more negative until 400. This is the range for stability. If you use K401 at 180 degrees, the magnitude will be positive. Then the system will be unstable. Any question? We learned an very important knowledge today about stability. And you should know that. It will be asked in the exam. Okay, this is from the book, from the textbook. This one I plotted by using MATLAB. This is taken from the textbook. The actual one is 6.16. We use 6.5 just now. The exact one is 6.16, and K is 378. We use we say K between 0 to 400. The actual one, if we calculate by hand, will be 378. Of course, it will be slightly different by using Bode plot and by using theory. Theory is like if by using Roth-Lewis, you can calculate also that value. It will be 378. But we can directly obtain from here, it is 400. If we use a better scale, then perhaps we can get the actual 378. Any question? If not, I will stop here. Tomorrow we will learn also another important specification in Bode plot called gain margin and also phase margin. It is also related to stability. These two quantity are also related to stability.